Hi everyone, so this is going to be our last lecture of differential amplifiers. So whatever the knowledge we have till now, based on that knowledge we are going to design an operational amplifier. So the first question is, what is an op-amp? What is an operational amplifier? So let's study about that. So this is the circuit symbol of an op-amp. This is how it will look in a circuit. So this is the circuit symbol. And what will be your V0? Your V0 will simply be A into V positive potential. V positive potential, this gain A into V positive potential minus V negative potential, that's it. So this is what it does, or you can write it in better manner, A into what is V positive, V1 minus V2, and if your V1 minus V2 is V in, if V1 minus V2 is V in, you can write like this. So it provides a high gain. This gain A is usually very high. So operational amplifier provides a high gain. Now in a circuit, how does it look like? Internally, how does it look like? So on a crude level, we can show it something like this. It has some input resistance Rin. It will have two voltage, V positive and V negative. V positive we have shown in the diagram by V1, and V negative we have shown in the diagram by V2. And V1 minus V2 we are calling is V in. V in. So whatever the V in that you are getting, that will be amplified with the gain A. Gain A. And then in the output you have a output resistance R0. This will be your final V0. Well and good. So basically internally this is how it looks like. So the box that I have made, internally it would be something like this. Ideally in the op-amp, Rin is very high. You can call it infinity as well, and R0 is very low. You can call it nearly 0. Why is it so? Because what will be happening is that you will be applying some Vs and Rs. Here you will be applying some voltage source. You are applying some voltage source. This voltage source will have some resistance. Now if Rin is very high, what will happen? Rin is very high. So how much voltage will be coming here? If Rin is infinity, then complete Vs will be coming at the V in, right? V in will be equals to Vs if your Rin is infinity. If your Rin is very high, it will eat up more voltage. So you want more voltage here. Now more voltage will be amplified. Let's just say Vs voltage is amplified. Complete Vs voltage is amplified. Now at the output you will be having some load. At the output you will be having some load. Now if this R0 is very low, then what will happen? R0 will eat up very less voltage. If this R0 is very low, R0 will eat up very less voltage, and more voltage will be going towards the load. Are you getting this point? If your Rin is very high, if your amplifier is having high input resistance, then what will happen? More and more voltage will come, and if your R0 is low, then it will eat up less voltage, and more voltage will go out at the output. More voltage will go at the output, right? Understood? So that is the reason that Rin is very high and R0 is very low. We will study all those amplifiers. When we study about the feedback amplifiers and feedback topology, we will revisit this thing. No worries about that. We will revisit it. So Rin is very high, R0 is very low, and gain A is also very high. Gain A is also very high, right? So what is an op-amp? So op-amp is simply a voltage controlled voltage source. This is a voltage controlled voltage source, right? Is a voltage controlled voltage source, or I should not write it in this manner. So basically you must have got the point. No, why do I need to write the definition of op-amp? We will repeat when we study about the op-amp as a black box, then we will study about it. So just in op-amp you are having a voltage controlled voltage source with low input impedance, with high input impedance and low output impedance. That's it. So it is a voltage amplifier actually. What is voltage amplifier? What is current amplifier? We will study about it. So basically it is an amplifier which has high input impedance and low output impedance. That's it, right? And one more basic thing we can study about op-amp is, let's just copy this diagram. Just copy this diagram. Forget about this V. Forget about this V1 and V2 as well. Let's just call this node as V positive and this node as V negative. So what will be your V naught? V naught will be A into V positive minus V negative. Say yes or no? A into V positive minus V negative. Now if your V positive increases, then what will happen? If V positive increases, then what will happen? Output will increase, right? If this node is increasing, certainly output will increase. But if your V negative increases, then what will happen? Output will decrease. Basic mathematics. If this is increasing, then more value is getting subtracted, then output will decrease. V positive increases, output will increase. V negative increases, output will decrease. Right? So this is the basic thing that we will be using later on in the lecture. So you need to keep it in mind. Well and good. So now what is our target? Our target is to design a high input impedance and low output impedance and a high gain amplifier. And one more thing we need to take care is that there should be two input and one output. So two ended input, two input, two input I should not write. Double ended input. I should write double ended input. Input can be one as well. Let's just say my input is V in. So what I can apply? V in by 2 and minus V in by 2. So input will be one only. I should write double ended input. Double ended input and single ended output. So double ended input and single ended output. Well and good. So this is what we need to design. So whatever that we have studied till now, based on that we will try to design that. So we have studied this basic differential amplifier. We can apply V in by 2 and minus V in by 2 and get some output. So let's just check if it is fulfilling our requirement or not. So let's first find the gain. Let's find the gain. First find what is our target. What we need to find. Change of color. First thing is we need to find gain. What is the gain? Gain, what do you mean by gain? V naught by V. Forget about common mode, all those things now. Just the gain. Gain will be V naught by V in. So for V naught by V in, you have applied V in here minus V in by 2 here. What will, and second thing you need to find input impedance. Input impedance. That you can see here is infinity only, but we will write it down later on. And the third thing you need to find output impedance. So these are the things you need to find. So let's start one by one. First, let's find the voltage gain. So this is our equivalent small signal circuit, right? First thing is gain. So we are finding the gain. So if this is V in by 2 and this is minus V in by 2, this is V in by 2, this is minus V in by 2, you can apply the Vx potential here and get to know the potential. What that potential will be? 0 only. Or you can apply the concept of half circuit as well. You can apply the concept of symmetry. If you apply the concept of symmetry, what this node will be? It will be grounded only. Why you can apply the concept of symmetric? Because both of the circuit are symmetric. One node is getting up, one node is getting down. So what will happen to this node? This node will be grounded. And if both nodes were same, then this node would have been open circuited. Now this node will be grounded. Well and good. Everything is crystal clear. If this node is grounded, then what is the current flowing here? That would be Gm V in by 2. All those things we have already seen. That's why we are moving a bit faster. So what will be V naught? V naught would be Gm V in by 2 into Rd. So what is your gain? V naught by Ve. That is Gm Rd. Right? And which is not very high. Not very high. Or you can consider in parallel, you can consider R naught as well. Right? In the parallel, you can consider R naught as well. But forget about it. So this is not very high. So first thing is we are failing here. Let's check other things. For getting a high gain, we can do other things as well. But let's check other things like am I getting a higher output impedance? So let's check about the output impedance. Before that, let's check the input impedance. What is the input impedance? So it would be V in by I in. So how much current is coming here? 0 ampere. How much current is coming here? 0 ampere only. V in by there is 0 ampere current. So input impedance is infinity. which is high, and this is what we wanted. We wanted high input impedance, right? High input, high input impedance. So this is what we wanted, that we got, and this was not desired. Let's talk about output impedance. Again, I can copy this circuit. So for finding the output impedance, what do we do? Forget about this, all those things. Finding the output impedance, we will short circuit the input. We will short circuit the input and measure R naught from here. So for measuring out R naught, what do I do? I apply a battery of V naught and get I naught out of it, right? Now I will ask you a question. Listen to the question carefully and answer me. Okay. My question is, can I apply the concept of half circuit here and keep this node as grounded? Did you understand my question? Can I apply the concept of half circuit here and keep this node as grounded? For getting the output impedance, this is my circuit. I am applying a battery of V naught here and getting I naught out of it. So my question is, by the concept of half symmetry, can I keep this node as grounded? Say yes or no. By the concept of half symmetry. No. Why is it so? Because your circuit is changed now. What was happening in this one? You have V in by 2 here, which is going up. This is going down. Going up, going down, same circuit. Then this is grounded. Well and good. What is happening here? Is that a symmetric circuit? What do you see here? RD and a MOS. What do you see here? RD and a MOS, but a battery of V naught which is having I naught current. What do you see this side? In the left hand side, RD and a MOS. In the right hand side, what do you see? RD and a MOS, and with parallel to the MOS, there is a battery of V naught which is getting I naught current into it. So you cannot apply the concept of half symmetry here. So this is the thing. I have seen n number of teachers saying that there will be concept of half symmetry, but no. I'm not talking about GATE educators. They don't even teach this concept. So forget about those. But many great educators, like those who have high degrees, those who are very much intellectual, they also did this mistake. They also say that you can apply the concept of half symmetry, but I don't think you can apply the concept of half symmetry here. Why is it so? Because the circuit are not symmetric. If the circuit are symmetric only, then only you apply the concept of half symmetry, right? So also you apply the concept of half symmetric when one node is going up, other node is going down, and you can break it from in between, and then that node would be grounded. If both of the nodes were going up, then the middle node would be open circuited. So that we have studied in the previous videos. So yeah, I don't think I can apply the concept of half symmetry here. So for now, I just have to keep it as a V exponential only, right? I will have to keep it as a V exponential only. So tell me, from Vx to ground, what do I see? From Vx to ground, what do I see? 1 by Gm, because R naught is not there. Let's just consider R naught as well now. Let's take lambda not equals to 0. So if I take lambda not equals to 0, tell me, what do I see from here? Your answer should be correct. What do I see from here? Gate is grounded. You are going from drain to source with some load resistance RD. You are going from drain to source, gate is grounded. What is the resistance? You are going drain to source, you are going backward, right? You are going from drain to source. You are going backward. So if you are going backward, you would need only one step. What is that step? That step would be Gm R naught plus R naught plus RD. Oh, and just brain fade. I'm really sorry. You are going from source to drain. It was a very bad brain fade from my side. You are going from source to drain. You are going from source to drain. Source to drain. So you need two steps. What are those two steps? R naught plus RD upon 1 plus Gm R naught. So this is the resistance you see from here, right? So basically I can reduce my circuit. I guess I have dealt this question in one of the previous videos. In one of the assignment we have seen this kind of question as far as I remember. But let's just practice once again. Now this resistance is replaced with R0 plus RD upon 1 plus GM R0, and this is your V out. Now tell me, what do you see from here? What do you see from here? You are going from drain to source. You are going from drain to source and gate is grounded. What is that resistance? That resistance would be, let's call this resistance as Rx. So your Rx would be, Rx will be, you are going from drain to source. So what is the resistance? GM R0 into this resistance, that would be R0 plus RD upon 1 plus GM R0 upon 1 plus GM R0 plus this resistance R0 plus other resistance R0 plus RD upon 1 plus GM R0, right? GM into R0 into this resistance plus R0 plus this resistance R0 plus RD upon 1 plus GM R0. Now you can take common R0 plus RD upon 1 plus GM R0, you can take it common. So if you take this common, what will happen? R0 plus RD upon 1 plus GM R0. You are taking common, so 1 will be coming from here and GM R0 would be coming from here. GM R0 plus R0. So GM R0 and 1 plus GM R0 will be cancelled. So your 2 R0 plus RD. This is the Rx value you are getting. So looking down from here, you get the Rx value, that is 2 R0 plus RD. And if you had applied the concept of half symmetric here, what you would say? Sir, VGS is gone, so from downward I see only R0. Is that correct? No, that is wrong. If you had applied the concept of half symmetry, you would say that, sir, both of the circuits are symmetric, so I can apply the concept of half circuit here, and if it is half circuit, this node will be grounded. If this node is grounded, that means VGS is gone, so from downward you see only R0. Is that right? No. From downward you see 2 R0 plus RD. So that was the glitch here. Because the circuits are not symmetric. It's not that you are applying Vin by 2 minus Vin by 2 here and the same circuit is there. Here you see RD and MOS, here you see RD and MOS and a battery of V node, because when you are calculating the output, you apply a battery of V node. So that was the best thing about this circuit, and we will encounter it again. So what will be your final R out? This is your R out. So I am writing your final R out here. So your final R out would be Rx parallel with RD, right? Rx, this is your Rx parallel with RD. So your final output would be Rx parallel with 2 R0 plus RD. Sorry. What is your Rx? Rx is 2 R0 plus RD only. 2 R0 plus RD parallel with RD. This will be your R out. And this can be nearly equals to RD only, because this 2 R0 will be a very high value. So your R out is nearly equals to RD, which is low. RD will be very low. You can keep RD to be low. So RD will be low. So this was the desired case. You wanted low output impedance. You wanted high input impedance. This is the desired case as well. But you wanted more gain, which is not high here. The gain is GM by 2 RD. I am really sorry. The gain is GM RD by 2. But you wanted higher gain. So that is the issue here. I wanted a higher gain. So for that, I use a different kind of circuit. That is this. I call this differential amplifier with active load. So what is happening here? We have again seen this kind of circuit already. We have already seen this kind of circuit in one of the questions, in one of the previous questions. So what I am going to do, I am going to apply Vin by 2 here and minus Vin by 2 here. And my target is to calculate V naught by V. So better we calculate it with GMR out method, right? I can calculate it with GMR out method. Why I am doing this method? Because with that I will be able to write down the R out as well. I'll be writing GM as well, and with that I will be writing R out as well. So let's find the gain with GM R out method. It will be easier as well, and we will reduce the calculations, right? So one thing there is to notice is that for this and this MOSFET, what do I call it? Let's just give them different names, M1 and M2. So for each of calculations, we will take lambda equals to 0 for M1 and M2, and lambda is not equals to 0 for M1 and MP. So this will make our analysis intuitive as well, and our calculation will also be reduced. So let's just take lambda to be very low for these M1 and M2. So R0 will be very high. So we are not going to consider R0 value. So let's find the gain of this circuit. Let's find the voltage gain. So we are going to find it with GMR out method. You can find it by the simple method as well, but I am going to apply GMR out method. So what I am going to do, let's just copy this circuit. So if you are finding the voltage gain, this VDD will be shorted, this ISS will be gone. This VDD is shorted, this ISS will be gone, and let's just find capital GM first. So if you are finding the GM, what you are going to do? You are going to short circuit this one. Can you apply the concept of symmetry? Can you apply the concept of half circuit? No, I cannot apply. I don't even see any half circuit here. I don't even see any symmetry. I cannot say that this and this circuit is symmetric. So I'm not going to apply any concept of half symmetry. What I'm going to do, I'm going to consider it as Vx. What will be the resistance here? The MOS are also different. Here it is having lambda equals to 0, and this is having a finite lambda, that is R0 n. And this is also having a finite lambda, that is R0 p. But this R0 p and R0, what is happening is that this you are having is R0 p. So this node is grounded and this node is grounded. So completely it is being shorted. Are you getting this point or not? So this R0 p is completely getting grounded. This R0 p is completely getting grounded, right? And from this node to ground, there is R0 n connected. From this node to ground, there is R0 n connected. So what I can do, so I will replace this R0. From Vx to ground, I can directly put R0, right? So let's remove this Vx for now. From Vx to ground, you are having R0 n. Did you understand this point? And this is Vx. From here to ground, you are having R0 n. So I put it like this. Now my target is to find this Vx. How can I find it? What is the current flowing here? And what is the current flowing here? Both the current combined will be going into this resistance. What I mean to say is that Gm Vin by 2 minus Vx plus Gm minus Vin by 2 minus Vx. This current is going into this resistance, that is R0 n, and this potential will be equal to Vx. Now if you solve this circuit, if you solve this particular expression, what will happen? Gm Vin by 2 and minus Gm Vin by 2 will be cancelled. So it will be minus 2 Gm R0 n Vx would be equals to Vx. So from here you are getting Vx equals to 1 plus 2 Gm R0 n equals to 0. So basically your Vx potential is becoming 0 only. So luckily you are getting Vx equals to 0 here. Here luckily you are getting Vx equals to 0. But that's not because of the concept of half circuit. No, this is not because of the concept of half circuit. Just you are getting by the calculation. there is no concept of half symmetric here. Just by the calculation you are getting it. So I will say this Vx is 0. This Vx node is 0. So eventually I am getting this Vx node to be 0 volt, right? Now how will I replace my circuit? Let's just replace my circuit now. Copy, then paste. So this R0N is becoming between two grounds. So this will be shorted. So this complete node will be gone, right? This is shorted. And similarly, this R0P is also becoming between two grounds. So this will also be gone. R0P will also be 0. Right? Basically what you can say, between here and here, this was your R0P. From here to here, this was your R0P, which is completely 0. This is completely 0. Everything is completely grounded. So there is no effect of R0P and R0N now. Right? Now tell me what is the current here. That current would be GMN, no, in the upward direction that current would be GMN V in by 2. What about the current here? That current would be, since this is also an NMOS only, this is also an NMOS, this is also an NMOS. So here the current would be in the downward direction GM V in by 2. Now the same current is flowing through M2 as well, because both are connected in series only. So the same current is flowing through M2 as well. That would be GMN V in by 2 only, right? Now both are having the same source and both are having the same source and same gate. VSG value is same. Source to gate, VSG value is same in both of them. And you are doing the small signal analysis, so this current can be simply copied here. So you can say that in the downward direction there is GMN only. This current only being copied. So here you are getting GMN V in by 2 current only. So what is the output current? One GMN V in by 2 current coming downward, and one GMN V in by 2 current is coming from upward. So what is the total current here? The target was to calculate this I out or ISC you can say. So your I out was GMN V in by 2 plus GMN V in by 2. So your I out would be GMN V in. So your capital GM is coming out to be GMN. That's it. So this is your capital GMN, right? Now what about output impedance? Now your target is to calculate output impedance. R out we need to calculate, because we are finding the gain. So now I will be calculating R out. So for finding the R out, let's forget about this Vx equals to 0, because this V in by 2 and minus V in by 2 will be gone. So now the equations will be completely different. These are gone. Forget about this R0P and R0. Now your output node is not grounded. This node is grounded. This node is grounded, but at the output node you are having some V node and you are getting I node out of it. And this is your R out. Well and good. Right, and forget about this R0N as well, because R0N is connected like this now. So this is your circuit. Now you need to calculate output impedance. So what I will do, I will first see the impedance looking downward. What I will do, I will first see the impedance looking downward, and then I will check what I can do. But tell me one thing, can you apply the concept of asymmetric and say this node will be grounded? Can you do it? No, that would be wrong. Why so? Because there is no half symmetric. In the interview, you can face this kind of question, that can you apply the concept of half symmetric for finding R out? No, that is absolutely wrong. Why so? Because the circuit is not symmetric. You are having a battery of V naught and getting current out of it. So the circuit is not symmetric now, right? So what you are going to do? You are writing the impedance. So tell me, from here to here, how much impedance do you see? Can you tell it is 1 by GMN? What is that impedance? 1 by GMN. Say yes or no. Because from this node to ground, you see only 1 by GMN because there is no R naught. The R naught is infinity here. The R naught is infinity because I told you for the ease of calculation, this side of MOS we are taking no R naught equals to infinity. So from Vx to ground, I only see R 1 by GM1. If you need to write the exact one, what you need to do? First, you need to replace this circuit. How will you replace this circuit? You will replace this one as 1 by GM, 1 by GMP parallel with R naught P. And then you will see from here, you are going from drain to, so you are going from source to drain. If you are going from source to drain, you will write R naught plus RL, this resistance, R naught N plus this resistance divided by 1 plus GM R naught N. So whatever the resistance I called it, the R. So that will be your final. But what we are doing, we are considering this to be very, very large. So that would be somewhat near to R naught N as well upon 1 by GM R naught N. And this is also very large, so basically your final output impedance would be 1 by GM. And if you don't want to do this analysis, what you just need to do? You just need to tell that from Vx to ground, what do you see? From source to gate, what do you see? 1 by GMN. That's it. So your impedance is 1 by GMN. Now I am looking downward. This is the task that I am doing. So looking downward from here, what do you see? Let's just call this as Rx. So what do you see as Rx? So for Rx, I will make a separate circuit. Here this resistance is 1 by GMN. 1 by GMN. And the gate is grounded. And from here you are looking Rx. From here you are looking for Rx. So what will be your Rx? For this one you are having R naught N as well. Remember it, you are having R naught N as well. So you are moving from drain to source. If you are moving from drain to source, you need only one step. So that step would be GMN R naught N into the source resistance, that would be 1 by GMN plus R naught N plus 1 by GMN. So Rx would be 2 R naught N plus 1 by GM. Since this 1 by GM would be very small, so approximately I can replace it with 2 RON only, right? So looking downward, this is my resistance, that is 2 RON, 2 R naught N. So from here you see 2 RON only. But if you had said that, sir, here this is grounded, so what you will see? What you will say, sir, from here to ground I see R naught N. That is wrong. From here to ground you see 2 R naught N. Exactly 2 R naught N plus 1 by GM. And very exact formula will be much different because you need to take this action, this in action that I told you. Like you can write down this potential, you can write down this resistance instead of this 1 by GMN. You can write down that big resistance that we wrote. So that you can write down and then you can apply this formula. So that will be very, very complex. So for ease of the calculation, we took R naught to be infinity for these two MOSes. So from here you see 1 by GMN, and from this node from Rx, what do you see? GMN into RON, GMN into RON into 1 by GMN plus RON plus 1 by GMN. So this GMN and GMN is getting cancelled. So 2 RON plus 1 by GMN, which is approximately equals to 2 RON. So from here to ground you see 2 RON. That's the scene. Say yes or no. Agree to this? No issue with that. Now I will make this circuit on the next page again. Arey yaar, I need to add up pages. Forget about this 1 GMN now. Forget about this. Forget about V naught. You are getting I naught here, right? And here you are having the impedance as well. That is R naught P. You are having the R naught P impedance as well, right? And this node is grounded. Now what I can say, from V naught to ground I see 2R1. From V0 to ground, at the downward side I see 2R1. From V0 to ground, at the upper side I see this resistance and this MOS. But from downward, what do I see? V0 by, and forget about this ground. There is no ground here. There is no ground here. Sorry about that. There is no ground here. So in the downward direction, what do I see? Vx, V0 by Rx, and Rx is 2R1. So what I can say is that Vx by 2R1 current I can see now. In the downward direction, I can see Vx by 2R1 current. Now the same current will be flowing like this, right? The same current will be flowing like this. Now the same current will be going into this MOSFET. So this MOSFET is also having Vx by 2R1. If there was a ground here, then what would have happened? This current could have gone to the ground as well. But there is no ground. There is no ground. It is just a simple loop. So from V0 to, why I am putting Vx? It is not Vx, it is V0 only. So from V0 to ground, since you see from V0 to ground, you see 2R1. So that means from this node to downward, you have V0 by 2R1 current, and that is flowing like this. V0 by 2R1 current. That is flowing in the loop. This current is flowing in the loop. Now, what is the scene? This is the source potential. This is the gate potential. This is the gate potential, and this is the source potential. Both of them are having the same VSG value. If both of them are having the same VSG value, both of them are having the same VSG value. So this MP MOSFET will drive the same current, and that current is V0 by 2R1. Are you satisfied this point or not? Are you satisfied with this point or not? What did I do? First, I started with this thing that people say that downward I see RON. That is wrong. That is absolutely wrong. Why it is wrong? Because this node is not grounded. If this node is not grounded, we will do the analysis. This is 1 by GMN and this is RON. So from this node to ground, I see 2 RON, not RON. So I see 2 RON. So now what I can say, from V0 to ground, if I see 2 RON, that means this, in the downward direction, I have V0 by 2 RON current. That's for sure. So if I am having V0 by 2 RON current, and that current will be flowing like in the loop. And whatever the current the M2 is having, the same current MP will have, because both of them are having the same resistance. That is, as both of them are having the same VSG value and same GM value. So both of them will have the same current. So the current is V0 by 2 RON. Oh, okay. The direction will be upward. I'm really sorry for that, because in the other MOS as well, the direction is upward. So in this MOS as well, the direction will be upward. Right? So direction will be upward direction, upward direction. Right? Now you can't say that, sir, this current is flowing in this loop. No. Why is it so? Because there is ground. There is ground mentioned. So what is the current going into the ground? V0 by 2 RON plus V0 by 2 RON, some current will be coming from R0P as well. That current will be going into the ground. So don't do this mistake. Right? So the current going into the ground would be V0 by 2 RON plus V0 by 2 RON plus V0 by R0P, because in the upward direction here you will be having V0 by R0P. So V0 by R0P. This much current is going into the ground. So don't do this kind of mistake that, sir, this current is coming and that will be flowing into the loop. Nah. Once you see the ground has the capability to drive some current. But there is no ground, there is open circuit, so this current cannot flow into the ground. It will just flow into the loop. Right? So this is just the ground current that I wrote. This is not a matter of fact for us. So what is the matter of fact for us? We need to find V0 by I0. This is the target. So let's check. What is the current coming out of V0? What is the current coming out of V0? So from V0, let's just check if you agreed with this point or not. In the upward direction, from V0 in the upward direction, look, this node is V0. V0. This node is V0. So in the upward direction, in the R0 P resistance, V0 by R0 P current is flowing. Say yes or no. V0 by R0 P plus in this upward direction V0 by 2 RON plus in the downward direction V0 by 2 RON, and that is equals to I0. So what is V0 by I0? So V0 by I0 over your output resistance is coming out to be R0 P parallel with R0 N. Can you solve it on your own? I guess you can solve it on your own. So it is V0 P upon ROP plus V0 P upon R0 N, that is equals to I0. So V0 by I0 would be ROP parallel with R0 N. So many of the students, what do they think that, sir, here it will be, you're finding R1. So here it will be shorted. So from here to ground I see R0 N, and from here to ground I see R0 P. So my output impedance is R0 P parallel with R0 N. R0 P parallel with R0 N. So that is absolutely wrong. This node is not this node is not shorted. There is no concept of symmetry applied here. There is no concept of symmetry here. There is no symmetry in this circuit. So this node is not shorted. From here to ground you don't see RON. From here to ground you see 2 RON. So just to remember, you can think like that. Okay, from here to ground I see RON, from here to ground I see ROP. So ROP parallel with RON. So usually people remember the output resistance of this particular circuit. Output resistance of this circuit. Usually people remember it. So there is a current mirror load. There is current mirror load, right? This is a current mirror. So there is a current mirror load, and at the downward you are having differential amplifier. So people actually remember ROP parallel with RON. But that's not the actual reality. The reality is from the downward direction you see 2 RON, then from V0, and this MOS is also driving the same current, that is V0 by 2 RON. This node is also driving the same current, that is V0 by 2 RON. So eventually we can apply the nodal analysis here. So from V0, what is the current coming? From V0, I0 current is coming. That current is equals to V0 by 2 RON plus V0 by 2 RON plus V0 by ROP. So the impedance is ROP parallel with RON. Certainly in the gate examination, someday they will ask you the resistance looking down from here. And if you say that is RON, that would be absolutely wrong. And even in the interview, usually when I take the mock interview, I always ask this kind of question, that what will be the resistance looking downward. And 99.99% student or 100% student, I have always heard the answer to be RON. But that is 2R1. So please do care of this kind of questions in the interview or even in the examination, right? So we have the GM, we have the R out. So what was our GM? GM was GMN. And what is our R out? R out is ROP parallel with RON, which is pretty high. And it was not desirable, not desired, because you wanted a low output impedance. So output impedance you are getting high, that is not desirable. What is the gain? Gain is GMN ROP parallel with RON. So this is the gain, which is high, and it was desired. And what is the input? What is the input impedance? Input impedance. Input impedance. Input impedance will be infinity only, right? Why it is infinity? Because from Vin by 2 there is no current. From Vin by 2 there is 0 ampere current. So input impedance would certainly be infinity. So this is high, and it was desired as well. High and desired. Now the only concern is this output impedance. The concern is this output impedance. So matter of concern. What is the matter of concern now? Is output impedance, right? This is the matter of concern. Now we have studied the differential amplifier with active load. Differential amplifier with active load. Can you remember the gain of differential amplifier with active load? That is GM and ROP parallel with RON. This you can remember. Well and good. So you will remember the gain, and you can remember the input impedance as well. That would be infinity. And what is the output impedance? Output impedance is ROP parallel with RON, which we got after a lot of calculation, not by the simply virtual short. Not by the simply, you call it sometimes virtual short. Okay, this node is virtually shorted. Sometimes we call it like that. So not by the concept of symmetry. We are not getting this by the concept of symmetry, but we did the rigorous analysis. We also saw that the current downward is V0 by 2 R1, not V0 by R1, right? So now our concern is this. What is our concern? Our concern is this output impedance, that is high. So we need a low output impedance. But before that, let's study bit more about this stage. A bit more about this stage, right? So this is VDD, and then there was a current source involved, right? I made a current source here. Let's just call this potential as V1 and this potential as V2. If I show this diagram, something like this, बैटरी बना लो यार थोड़ा डायग्राम. If I show this diagram like this, is there any issue with that? Am I calling it an op-amp? No, this is not an op-amp. Not an op-amp. Why is it not an op-amp? Because it is having high output impedance, which was not required. It is having high output impedance, which was not required. So this is not an op-amp, but I can show it like that. Look, what will happen if V1 increases? What will happen? From here to here, this is common drain. If you are going from gate to source, there is no inversion. There is 0 degree phase shift. Do you remember this thing? From here to here, there is 180 degree phase shift. And from here to here, there is 0 degree phase shift. I hope you remember this thing, right? So, if this node increases, then this node will increase. And if this node increases, what will happen to this node? This will also increase because from here to here, there is 0 degree phase shift. So if this node is increasing, the final output is increasing. That means which one will be V1? Tell me, this or this? If V1 increases, then V0 is increasing. So which should be V1? So V1 has to be V positive 1, right? So V1 has to be V positive. Why is it so? Because if V1 increases, then output increases. Understood? Right? We studied it in the op-amp that A into V positive minus V negative. So if I am showing this circuit with this sign, that means if the positive one increases, then output should increase. So if the positive one increases, if V1 increases, the output should increase. What about V2? Let's see about V2. So let's see about V2. If V2 increases, from here to here, what will happen? From here to here, there will be 180 degree phase shift. From gate to drain, there is always 180 degree phase shift. So if V2 increases, then output decreases. If V2 increases, then your output decreases. So what will be your V2? V2 will be this V negative. So this will be your V2. Well and good. If V2 increases from here to here, there is always 180 degree inversion. So if this increases, that will decrease. Right? So V1 is positive, V2 is negative. This concept can be used many times in the questions as well and in the interview as well. So when I was giving the interview for my intern, this question was asked to me. Okay, in the internship, this was asked that I needed to show the sign of positive and negative. And in the gate examination this year in 2024, this question came that they shorted the output to this node. So what did they actually do? They just made this circuit and they gave the gain of this one. They gave the gain A value. So they asked the output voltage. What that output voltage would be? V1 minus this node is shorted. So V1 minus V0 into A is equals to V0. When you solve this one, you get V0 equals to A upon 1 plus A. A value you already had 40, that was given 40 by 41. So that would be your answer. So usually when I teach analog circuits, I always teach this active load differential amplifier. But yeah, this was asked this time in the examination. Even in the internship interview, this was asked to me that which sign will be positive, which sign will be negative. So and in the examination, what they did, just sorted it. Now many teachers are claiming that it was there in their notes, but I have seen their notes. It was never in their notes. Forget about that. So I hope you have understood this point that if V1 increases, this node increases, that node will increase. So positive node will be V1. What about V2? If V2 node increases, then V0 node will decrease. So that negative node will be V2, right? So, but this is not our op-amp. This is not the op-amp that we have designed. For op-amp, we need low output impedance. We need low output impedance. So for getting low output impedance, what you will use? What do you think? We have studied different topologies. Let's check them one by one. Common source. Can we use a common source amplifier? What is the gain of common source amplifier? If you remember, gain and issue is output impedance. What is the gain? Gain is GMRD, right? And what is the output impedance? GMR0, you can say. Gain is minus GMR0 and output impedance is R0, high, right? This was our common source amplifier. Very quickly I am going to write it down. Right, high. You cannot use it for output impedance because we need low output impedance. Then at the next stage I am going to use some other amplifiers. What about common gate? Common gate. This was grounded. This is your V in. Let's just say this is your load RD. Right? This is your load RD. And better you call it this from here to here. There is this R not connected. And this is your V naught, right? So approximately gain comes out to be GMV in this current. So GMR naught V naught V in plus GMR naught V in 1 plus GMR naught it would come, no? This was the approximately you can say GMR naught only or 1 plus GMR naught also you can write 1 plus GMR naught. This is the gain you are getting. And what is the output impedance? Output impedance is R naught. That is high, right? Output impedance is also high. What about common drain? Common drain. So for common drain, this was common drain. Sorry, at the source you were, at the gate you were applying V in, and the gate you were applying V in, and this was your R naught, and this was your V naught. Gain was pretty low, nearly equals to 1 only, or you can write GM nearly equals to 1. Otherwise, people will take it. So gain was GM R naught upon 1 plus GM. You don't need to mug it up. You can derive it in 1 second only because we have enough practice, and that is nearly equals to 1. The gain is not high, but what is your R naught? What is your R out? R out is R naught parallel with 1 by GM, which is nearly equals to 1 by GM, and that is low. Your R out is low. So there was the differential amplifier with active load. In the output you can use a common drain amplifier. If you use that common drain amplifier, what will happen? Your output impedance will be low and it will not change the gain. But my gain is this: GMP R0P parallel with R010. Doesn't seem that high, right? It does not seem that high. I want a higher gain. I would need a higher gain than this. So it doesn't seem to me that much high. What I am going to do? I am going to put for increasing the gain, I am going to put one more stage, and that stage will be common source amplifier. So here I am going to put one more stage, that would be common source amplifier. This is the common source amplifier that I am going to put. This is VDD. So this is the load, and then from common source amplifier I am going to put a common drain amplifier. common drain amplifier. In the output, as the load you are using a current source. In the load you are using a current source. I told you in the load you can use anything. I am using a current source. In the load I am using a current source. So first I put a common source amplifier using PMOS, and then I am putting a common drain amplifier. Common drain amplifier. And here I am collecting my final output. So what was this stage? And this will be your Vin by 2 and minus Vin by 2. What was this stage? Differential amp with active load. With active load or current mirror load. What is this stage? Common source amp to increase gain. Now the question comes, sir, the gain of common source and the gain of common gate is nearly the same. Why don't you put common gate? Think about it. First think about it. Why don't I put common gate? If I put common gate, what will happen? From this node will be connected to common gate. So this node will be connected to somewhat like this. This is your common gate, right? This is your common gate. So this node will be connected to this. Now at the load, what I would see, R0 P parallel with R0 N, parallel with 1 by GM. R0 P parallel with R0 N, parallel with 1 by GM. So here my output impedance will decrease. So it will decrease my gain. So I'm not going to use common source. I'm not going to use common gate here. I'm going to use common source amplifier. So common source amplifier to increase the gain. Why I'm not using common gate? The reason being, it will needlessly load my output. It is loading my output with 1 by GM resistance. If it is loading my output with 1 by GM resistance, my final output will be decreased. And this is not what I want. I want to increase my gain. So this is how I increase my gain. And now then I use a common drain amplifier, common drain amp or source follower you can say, because it has lower output impedance. So basically this is our desired op amp. So now you can say, I'll draw it more clearly this time. So this is our op amp. Yeah, so let's just write the gain first. What was the gain here? GMN ROP parallel with RON. And if you go from here to here what will be the gain? The gain here would be, this gain will be multiplied GMN ROP parallel with RON. This will be multiplied with Vin GM of this GMP and R out of this, that would be ROP, right? This would be multiplied, and then from here to here there will be no change in gain. From here to here there will be no change in the gain. The gain will be nearly the same, but input impedance, what is the output impedance looking from here? Output impedance. So here our output is 1 by GM. Nearly I should write 1 by GM. Our output is nearly equals to 1 by GMN, which was desired. What is our gain? This is our gain. Gain is equals to this much. This is the gain. This was also desired. And what is the output? What is the input impedance? Input impedance is infinity. Input impedance is infinity, which was also desired. So all the desired we are having. So this is our op amp. And why it is called two-stage op amp? This was the one stage, first stage, and this is the second stage. So two-stage op amp. So this is the op amp that we have designed. We targeted for a higher output. We targeted for a higher gain, low output impedance, and higher input impedance, and that we have achieved. Now my question will be, let's remove this one. Let's remove this. Let's call this one as V1, this one as V2. Which one will be V1, which one will be V2? and here you are having this final output. So you have replaced this box, this complete box, with one dabba, with one box only. You have completed this complete circuit with the one box only. So which one will be V1, which one will be V2? This is my question. Think about it and then let me know the answer. Let's start. If this increases, what will happen to this? This will increase. If this increases, then this will increase because there is no inversion. Now, this is common source amplifier. From gate to drain, there is always inversion. From gate to drain, GD, group discussion. When there is group discussion, if there is GD from gate to drain, if you are going, if there is group discussion, what will happen? Your knowledge will decrease. So never do group discussion. Just joking, just a way to remember. So if this increases, then this will decrease. And if this decreases from gate to source, there is no inversion, so this will also decrease. So if V1 increases, your output is decreasing. So what will be your V1? This will be your V1 and this will be your V2. And this is actually an op-amp. So in the examination that was asked, this question was asked, it was not actually an op-amp. This is an op-amp. So in op-amp, if V1 increases, this node increases, this node will increase, this node will go down, this will not go down. So this is V1. What about V2? You can check for V2 as well. If this node increases, then this node will go down. Gate to drain, there is an inversion. Then again gate to drain, GD. If this node goes down, this node will go up. If this node goes up, this node will go up. Because from gate to source, there is no inversion. From gate to source, there is no inversion. So if V2 is going up, finally V0 is also going up. So V2 will be this V positive. So this is the op-amp design that we have done, and that was the required one. Right? Now, what is the scene is that you can replace these ISS current sources, with the MOSFET. So we are going to make this ISS current sources from the current mirror circuit. So this is the current mirror circuit you are having. ISS current is coming and that same current ISS will be flowing here. So the same circuit is there, nothing is different. Same circuit is there. So ISS current is flowing. So this is the final design that we have made. This is the final design that we have made. This is our final op-amp. Now go back to our first lecture of network theory. Introduction lecture of network theory. Course curriculum. In the course curriculum, in the last slide, I told you that we will start from charge and we will end with this. And in this circuit, you will know everything. What is the current? What is the gain? Why do we put this particular transistor? Do you know everything? Yes, you know everything. So I fulfilled my target. I told you I will start from simple charge and I will end at this particular circuit and you will know everything in this one. And you know everything. Now you have designed a op-amp. You have a designed and two-stage op-amp. One more thing I would like to add is that this is not an ideal design. When you become a chip designer, this is not relevant neither to placements, neither for your interview, neither for your gate examination. But when you become a chip designer, there will be a lot of issue with this design, so you will change it accordingly. You will change. In case of common source amplifier, sometimes you can use a cascode for getting high gain. In the case of common drain amplifier, you can use something else. Then you will be studying more topologies. But for now, the basic design is this, and I hope you are able to understand it. Well and good. Now you have designed an op-amp which looks something like this. With this being the output voltage, there are two nodes. So V positive, V negative, this was V2 and this was V1. Well and good, no issue with that. So I hope you have understood the lecture. From where we started with the simple thing that I need to design this op-amp. Then I got to know that whatever that I have studied, that is not enough. From then I got to know about this topology, that that differential amplifier with current mirror load. If differential amplifier with current mirror load, for that I saw some interesting thing, that was that here Vx was coming out to be 0, so my Gm was Gmn, and from upward Gmn Vin by 2, and from the upward direction also Gmn Vin by 2 was coming. So total Gm was Gmn only. Also I could see that yeah, this Vx was coming 0 only, and then I got to know about the R out. So in R out, many people say that this node will be grounded, but that is absolutely wrong, because from V0 to downward, I see 2 RON, not RON. How did I get it? By the simple derivation. For the calculation purpose, I am taking lambda equals to 0 for M1 and M2. So from downward, I am having 2 RON. So V0 by 2 RON plus V0 by ROP, V0 by 2 RON plus V0 by ROP plus V0 by 2 RON is equals to 0. So V0 by ROP plus V0 by RON is equals to I0, sorry, is equals to I0. So my final R out is ROP parallel with RON, which is high, and this is not desirable. So this was not desirable, that was an issue. My gain was high, that is desired. Input impedance was high, that is also desired. So now to resolve the issue, before resolving the issue, we saw one thing, that if V1 increases, your output is increasing. So you can replace it with the this positive sign will be V1 and this negative sign will be V2. But this is not an op-amp. This is not working as an op-amp. Why so? Because in the op-amp you needed a low output impedance, but here you are having high output impedance. So this is not an op-amp. So now you need a low output impedance. You need low output impedance. For that you are going to use a common drain stage, because in the common drain stage you have low output impedance. For increasing the gain, you are going to use common source stage. Why you are not going to use common gate? Because common gate will load your output at the first stage. So you don't want that thing. That's why you are going to use common source. If you are using common source, your gain is also increasing. Also, with the help of common drain, you are getting low output impedance. Your output impedance is low, that is equals to 1 by Gm. So you have got your final design that looks something like this. And in that design, for using ideal current, in place of ideal current source, you will make those current source using the current mirror. So this you will get from band difference circuit. This ISS you will get from band gap difference circuit, and then these current sources you will make, and this will be your final output. So this is how your op-amp looks like. Now what you are going to study? We are going to study this op-amp as a black box. You will do a lot of things with this, and then you will study about it. Now you will connect resistance, you will get the gain, you will get the gain A. Here you are having a gain A, that is pretty high. So you are going to play with this IC. Now you have designed this particular integrated circuit. Now you are going to play with this integrated circuit, right? So in the next lecture onwards, we are going to study about op-amp. But I will think first I need to teach you op-amp, or I should teach feedback topology. Because if I teach feedback topology, that would be more helpful for you. So let's see what I am going to teach in the next lecture. Okay, thank you. So till now this much is completed. I expect a like from your side. Okay, thank you.